Okay, so in the proof of star, we have already got the following identity, which is given here. So we have been able to write this joint probability, which involves the x tildes, in terms of probabilities about x's and an integral with respect to that. Okay, like this. So the x tildes are all gone, the x's, and then we have also been able to write them in terms of an integral. And integrals are all about the random variables which follow exponential and gamma, as we saw in the last slide. Let's quickly go back. Sn follows a gamma with parameter n and alpha, and all the x's in the integral. Sn follows gamma, so this density would be gamma density, and all of these would be survival function of exponential alpha evaluated at different points. So we'll do that in the next step. So if you do that, this is what you're going to get, except that I'm not going to write down the gamma density. I'll just write it as FSNU. It's a gamma density, but we are not going to write it down. So, but all the survival functions of exponential at different points, these are all exponential, xn plus 1, xn plus 2, xn up to xn plus k, all exponential random variance parameter alpha. So the survival function would be just e power minus alpha times the point here. So e power alpha minus x2, for example, will equal this guy. E power minus alpha xk will equal this guy, and so on. Similarly, this one would be e power minus alpha multiplied by t naught plus x minus u in the bracket. So this whole thing would be like that. And then if you write things nicely, you see that first of all, this integral is over u. The u is only available here. Everything else is just x's. So let's take them out, including e power minus x1 from here. If you take them out, you already see what you're supposed to get in the right-hand side, a part of it. Okay, so that's already a good sign. So you already see the product of e power minus alpha xj's are coming out. And then the rest is a 0 to t naught integral of e power minus alpha t naught minus u fsnu du. Now what is that? Let's try to recall what that is. Now this, I can write it in many ways, but I'll deliberately I'll write this. This is again e power minus alpha. This is essentially the survival function of an exponential random variable, and actually came out of, it's a part of xn plus 1 bigger than this. One part has been taken here, so but this is still xn plus 1 bigger than t naught minus u. And since u is less than or equal to t naught minus u is still positive, so therefore this is the probability of xn plus 1 bigger than t naught minus u multiplied by fs and then integrated. Okay, so this is what we achieve in this slide, in this calculation. So let's try to start from there. Now this, I haven't written the density of Sn explicitly, which I could have done, but I didn't do it. There is a reason behind it. I'll write one more step just to remind you. I'll deliberately write this unconditional probability as a conditional probability. Namely, I'll condition on Sn equal to u, or Sn being very close to u. Now, of course, this conditioning is a joke because xn plus 1 is independent of Sn. Sn is a function of x1 to xn, and xn plus 1 is after xn, and all the xi's are iid. So therefore, Sn is independent of xn plus 1, and therefore this conditioning is just a joke. But once you see this conditioning, you'll be able to recall that this is precisely equal to this probability, this integral here is equal to the probability, the joint probability that Sn is less than or equal to t naught, which is because you're integrating this whole thing from 0 to t naught, and xn plus 1 is bigger than t naught minus Sn. So if Sn equal to u, then you're exceeding xn plus 1 by t naught from you're calculating the conditional probability of xn plus 1 bigger than t naught minus u. So therefore, when you uncondition this thing, when you integrate this whole thing, so by this continuous version of law of total probability, you get xn plus 1 bigger than t naught minus Sn. Okay. So we actually reverse this step, in one of our calculations earlier. So we wrote this is equal to this before, but now I'm reversing that previous step that we had. Okay, so now let's write this nicely. We know that Sn plus Xn plus 1 is just Sn plus 1. So if we do that, we just get, this is the probability of Sn less than or equal to T naught, which is in turn less than Sn plus 1. Now, of course, in all of these steps, this product of exponentials remain the same. We didn't even touch it because this is one of the things that you are supposed to obtain. So we don't want to touch that at all. Now observe that Sn less than or equal to T naught, which is strictly less than Sn plus 1, is same as, so this is same as saying nth arrival. This is precisely nth arrival comes before, on or before time T naught, was n plus 1th arrival times comes after time T naught. So therefore, this just means that the number of arrivals up to time T naught is precisely equal to n, exactly equal to n. So that's exactly n T naught equal to n. So we have actually achieved what we have to achieve. Okay? So this proves star. So star is proved. Okay, so it was a long calculation, but at the end of it, we have been able to show star. And in particular, this finishes the proof of the theorem, because star immediately implies A and B, as we have observed. And from A and B, the theorem follows. So this proves actually not just star, it proves the theorem as well. Okay, so let's take an example. Since we have been talking about so much of theorems and theory, so let's take an example. Suppose there is a salon and the customers arrive in the salon according to a homogeneous Poisson process with rate alpha equal to 4 per hour. Okay. Suppose the salon opens at 7 a.m. and the owner decides to take a nap between 1 p.m. and 2:30 p.m. provided there is no customer in this period. Okay. Now you may ask, why would the owner do that? The answer is very simple. Maybe the owner is a Bengali. He wants to take a nap after having rice. Sorry for this bad joke. But other than Bengalis, also Spanish people also take a noon siesta. So maybe the salon owner is either a Bengali or a Spanish person. Okay. Now suppose this is the goal that the owner has. Of course, he or she can take a nap provided there is no customer in this period. Okay. Now the question is, what is the probability that the owner would actually be able to take a nap in this period? Okay. So let's first try to write them in terms of the notation that we have been using so far. Let NT be the number of customers that arrive during time 0 to t. Now the time here would be in hours because the rate is given as 4 per hour. So the time unit is already specified here in the rate. So it's the time unit is in hours. Okay. So let NT be the number of customers that arrive from 0 hour to t hours, where t is bigger than or equal to 0. Now here, of course, 0 means 7 a.m. That's a starting point. And of course, hours here is not just an integer. It can be a fraction. Okay. Then it's given that NT is a homogeneous Poisson process with rate alpha equal to 4. Okay. So the fact that it's given per hour has been already incorporated in the unit. So this is the NT is just a Poisson process with rate alpha equal to 4. So therefore, the required probability, which is the probability of the owner can take a nap between 1 p.m. to 2:30 p.m., is that the probability that no customer arrives between 1 p.m. to 2:30 p.m. Now in this scale, if you start 0 is 7 a.m., what would be 1 p.m.? That's 6 hours from 7 a.m., right? So therefore, 1 p.m. is the 1300 hours, so that's exactly 6 hours. So from hour number 6 to hour number 7.5, there should not be any customer. That's what we're asking. So we are asking, what is the probability that number of customers arriving in the period 6, 7.5, okay, is 0. Okay, which is, well, when I write 6, 7.5, it's a semi-open interval. It's open on the side of 6 and closed on the side of 7.5. So this is same as asking the probability of n7.5 minus n6 is equal to 0. Okay. So in our notation, this is what we have to calculate. So therefore, what we have been able to do is we have just converted this into a problem of Poisson processes. So we start with a Poisson process whose rate is alpha equal to 4. And we just have to compute probability of n7.5 minus n6 is equal to 0. Okay, which is saying that no customer arrives in the period 6 to 7.5. Okay. Now apply the theorem with t naught equal to 6 to get that n tilde t, which is n of 6 plus t minus n of 6, is also a homogeneous Poisson process with alpha equal to 4. Okay. So therefore, the required probability, which is this guy, is just n tilde 1.5 equal to 0. So this probability is just n tilde 1.5 equal to 0. Now n tilde 1.5, this is a Poisson process with rate alpha equal to 4. So therefore n tilde 1.5 is just Poisson with parameter 4 into 1.5, which is parameter 6, Poisson with parameter 6. So you're asking a probability of Poisson with parameter 6 taking the value 0, and that should be e power minus 6. Okay. So therefore, we see that the probability of the owner taking a nap is actually pretty low here. Okay. So therefore, the owner get a period of 1.5 hours where no customer will arrive is actually quite unlikely. So either the Bengali or the Spanish owner would not be able to take a nap here. So one thing I would like to point out is that, I just gave you that the customers arriving in a salon is according to a homogeneous Poisson process. And this may not be a very good model. Okay. So see here, we saw that the homogeneity comes in the fact that, from 1 to 2:30, no customer arrives. So in this calculation, we saw that ultimately what matters is the length of this interval. 7.5 minus 6 was 1.5, and that's all that matters in the calculation. Where the length is, whether it's from 1 to 2:30 or it's from 7 a.m. to 8:30 a.m., it doesn't matter. Even if I had a question which says the owner wants to take a nap from 7 a.m. to 8:30 p.m. in the beginning of when the salon opens, the answer would be the same. Even though the chance that there will be customers from 7 to 8:30 is much lower, should be much lower than that there will be customers, from 1 to 2:30 p.m. So therefore, perhaps using homogeneous Poisson process is not a good idea here, because homogeneity may not be a good assumption. So here homogeneity means wherever you go, what matters is the interval of time. So there's a homogeneity across time. Okay. So we'll make it more precise later. I just wanted to give you a prelude. So here one should actually consider what is called an inhomogeneous Poisson process. But we'll talk about it later. We'll just have a brief slide on that. Okay, so this brings to the end of the second lecture. So if you have any question, feel free to ask me, or otherwise we'll again meet on the next class, which is on Monday. So thank you very much.